And hello, welcome everyone. So let's jump to the cut straight to the chase. So last time we were here talking about tests and how derivatives will be tested, as well as how I will potentially want to test the Churchill correlation code that I want to have. Alright, so yes, next thing is writing actual code, or at least talking about philosophy of how I would like to write the actual code. So here we are. Let's go to besides the fluid pipe theory. Okay, I do have this thing called pipes and valves. Okay, pipes and valves. readme.md. Yeah, readme not markdown. So pipes and valves has a readme markdown file. Okay, and this will kind of show how I want to write the code. I've written a bit here, quite a fair bit about code design philosophy, why I design the code certain ways. And of course, I think I will write the C# code along with I'll write the C# code along with what comments and how I explain the code as you go along. As of now, it's still incomplete, but I'll just document what is already there as of the time of recording this video. Okay, so code design philosophy is as such. Okay, pipes and valves. The whole purpose of this code is to act as a component that can be put into a regular circuit. Okay, a circuit is actually an IEntityCollection. An entity, as we explored before, is actually the class. Okay, IEntity is the interface. Entity is the class that components actually inherit from, and every other component like cells, resistors, all of that will inherit from components. So you actually stuff components into this IEntityCollection, which is over here just a circuit. Okay, as far as possible, the next thing is that because of our object-oriented programming, when I do object-oriented programming, as far as possible, I will be using solid principles, dependency injection pattern. I assume you know what they are. Okay, I'll be using the factory pattern to instantiate objects if there's a lot of dependencies that need to be injected. Okay, what's factory pattern? Well, in the solid principles, there's this thing called single responsibility. So, and the whole idea of loose coupling. So the fact that okay, I assume you know what it is, so I'll just refresh your memory. Yeah, factory pattern means that, so I have a class that has like maybe 5 dependencies. Okay, I can choose which dependencies are injected into the constructor for constructor injection. However, that makes instantiating the class very troublesome. So I'd rather have another class to take care of which dependencies to assemble to inject into this class, so that it sort of assembles the class together with its dependencies, and then returns it to what I want to do, returns it to the environment. So that's the whole idea of a factory. Okay, so so factory pattern. Okay, this is the factory pattern. I'll just use the tutorials points one, but it's not only for that. Okay, so you can see the very simple example, not that realistic compared to real world. In the real world, object-oriented programming is sometimes overkill for everything. So I tried this out before, and I found some of videos on YouTube that show that this object-oriented programming and using solid principles for everything, abstractions, is quite overkill. So it's like how far do you want to carry solid principles? And as we've seen in the in our code exploration of SpiceSharp, well, it's written very nicely using solid principles. Admire the author for trying to structure the code. It can make it very hard to read sometimes, and as a result, I could not actually figure out where how classes interact with each other. because of these things like events and auto-generated code and everything like that. It makes it, and dependencies just go all over. They kind of go all over the place, even though there's attempt to use dependency injection. But you know, sometimes the thing like, you know, what is an entity, what is IEntityCollection, there's so many class types, interface types, that it's just very confusing. So there is a school of thought that says solid principles are sometimes overkill for code that doesn't really need to change. In fact, overdoing can obfuscate the code, meaning to say it makes it extremely hard to read. There are two of these YouTube links that are very good. I mean, you can take a look at my readme in a markdown in a spiceSharpFluidFLowSolver, spiceSharp, or maybe you just look at my GitHub, and I'll go to the repositories, and you will just see spiceSharpFluidFLowSolver. Okay, spiceSharpFluidFLowSolver, go to documentation. Alright, go to documentation, and you will see pipes and valves. You'll see this readme being displayed here. Okay, these are clickable links here which you can go and look in your own time. Yeah, why object-oriented programming is bad, that's one. And you can go and see
argument marshal.
Why object-oriented programming is embarrassing, 4 examples. So this is actually made by a person who is very experienced, much more experienced than I am. So he's saying that it's not necessarily good to have object-oriented programming all over the place. It can really make things confusing and burn a lot of time unnecessarily. So there are 3 programming styles so far. Solid principles pertains to object-oriented programming, and lately we have learned we are seeing more functional programming, where functions are where you don't really make objects anymore. You don't make objects the centerpiece or the smallest thing in your program, or the world doesn't revolve around objects, but instead in functional programming we just are interested in making functions and using functions as is. Okay, and we don't bundle functions as much into classes and use them within classes. Well, I mean, you can do that, but I mean, that's not the point. Functional programming wants you want to use functions, and as far as possible, all right, the way it's done is that one function should always function the same way. The function should always return you the same result for given inputs. For object-oriented programming, that isn't quite possible. So for example, let's say I give you this example. If maybe I'll go through some examples later. Okay, but it's a bit hard to say this without example, but I'm going for like general things, general overview. Okay, especially if you code before, you find that solid principles are a little bit overkill. Functional programming is this next school of thought, which is often used in web development and all that, JavaScript nowadays. Okay, but functional programming, the nice thing about it is that you don't have to instantiate classes, but more importantly, the same inputs will always give you the same outputs. So the code is very nicely segregated. There's no mistake about it. Okay, if you have a function that returns the Reynolds number given a Bijon number, it will always do the same thing no matter what. Okay, always behave the same way. Whereas if the function is in a class, sometimes the function will depend on some variables in the class. Okay, so that kind of makes it confusing, but more on that later. Okay, so these are the third tool, of course, is procedural programming. Procedural programming is just writing your code without very much functions or classes at all. It's just writing code like with if-else loops, and you declare variables, you do stuff to the variables, not very much classes if at all, or not very much functions if at all, and then you just do everything and be done with it. Okay, there are strengths and weaknesses to each of these. So let's just go through some of them. Okay, I've looked for this blog and I paraphrase some of the strengths and weaknesses of each programming style here, and I'll cater this. I will not be using any one pattern in my code, and yeah, I will use each code where it's suited best. Okay, so what is object-oriented programming good for? It's good for reusability, because I can reuse classes and objects over and over again without rewriting the same code over and over. Okay, there's inheritance we can use. Okay, this is security. If you design it right, some functions and classes, well, they're not meant to be used by the outside user, so we kind of can hide them away during normal runtime, during the execution of the code. All right, so if there is some intermediate piece of code, like there's this for loop I want to do. Okay, maybe I'll use examples later. Okay, if I ever, no promises that I'll come back to this point, but yeah, just hold it in there. If I come back, I come back. Okay, but most important here is maintenance, right? Okay, supposing that you already are familiar with the code, it's easy to swap out one dependency for another because of dependency injection and loose coupling. That's to do with solid principles. Now that's a very strong part of object-oriented programming. It allows you to swap dependencies in and out, and that's a strength actually. Okay, what is not good is because you need a lot of planning. As you might have known, object-oriented programming, you'll see dependencies flow all over the place. Okay, you need to plan out your interfaces, how each class actually depends on interfaces and all of that. So, and then you have to think about factory designs and sometimes even the context and stuff. If you don't know, yeah, you kind of get the idea. It's too complicated. And object-oriented programming takes much longer to read, and you need to jump between parts of the code. As you can see, when I was exploring SpiceSharp, it's very beautifully written in the solid principles, but well, that means I just need to jump across many classes. Now, if the how do you say, inner workings of the code were all in the same file, it's easier to read but very hard to debug. Okay, it's easier to understand but harder to debug because all this stuff going on in the same file. It makes it very hard to debug what's actually going on. And if you have files thousands of lines long, it's also pretty hard to read. Okay, it is not that good as well. So that's the thing about object-oriented programming. Okay, for procedural programming, what's good? What is it good? Okay, procedural programming is very intuitive to read. Okay, it's easy to track the flow of data from one function or one part to another. All right, in procedural programming, all the inner calculations will be all put on the same page. So if you have a Newton-Raphson method, you will actually write the code to perform derivatives in line, meaning to say you put the derivation code here, a derivative code here for differentiation, you put the function you want to differentiate there, you maybe add a few comments here and there. So it's very easy to read. Okay, easy to read, but of course when you program it's a bit harder to debug because there's so many moving parts within a single file. Okay, so what is it bad for? Okay, you cannot really reuse the code here in procedural programming. So if I write my derivative code here, if I make a code here to do central difference approximation or some sort of integration, I cannot really use it in other parts of the file because it's not bundled up in a function. So if you want to do big programs and stuff, it's very hard to scale up. So that's why you don't really use procedural programming for humongous programs, and you don't stuff all the things into one file. It's okay for the computer, it's not okay for humans to read. So maintenance will be a nightmare if you need to change parts of the code, right? So it's not very modular. If you need to change the way the derivative works, for example, you might just end up breaking the whole piece of code from something that's working to something that's like not working. And then not only that, if you want to fix that up, you need to either use more time or if you cannot fix them up, then it's kind of done for you, unless you save a backup, of course. Okay. So what about the last one? Okay, the last paradigm I want to discuss now is the functional programming. What's the strength? Okay, pure functions are easy to test. Okay, what are pure functions? For example, if you pure functions are just they're just the simplest kind of function in the sense that they are standalone. If you have a function that takes in two parameters, for example a multiplication function, the return will always be the first input times the second input. There's no two ways about it. Whatever you put in there, it will just keep returning you the same thing. These are very easy to test, and they're very modular. Okay, you can still reuse bits of the code as well. Okay, information is explicitly passed through the function, not the result of some event or whatsoever. So that's the philosophy of functional programming. You want to pass information in explicitly into the function. Okay, and you do not set the state of the object. For example, I give you let me go to Ranger. Okay, this is a text file manager. It's very interesting. I just found out this thing. So I'll go to spiceSharpTest. All right. Okay, so spiceSharpTest. We'll go to the custom resistor, and we'll go to maybe this non-linear resistor. Okay, so I'm opening up this non-linear resistor.cs or non-linear resistor test.cs. Okay, you can see all the preview is already here. You see that for classes you can use this thing called the set parameter. So you're changing a variable within this class. Okay, you're changing a variable within this class, and that will change the so-called state of the object. Whereas with functional programming, you don't do that at all. You just have a function that has a certain input and a certain output. It will remain same for all the time. So when you play with objects, you need to be very mindful of the state. For example, in this case, nonlinear resistor, you need to keep track of how you set the parameters, or how you inject things into the constructor. Okay, well, those are good in the sense that you don't do too much in one line. It means that you have to keep track of all these changes. Now, for a few classes and a few objects, that's fine. If you have 10 or 20 objects and you keep having to keep track of all of them, it will be a nightmare. Yeah, but so yeah, that's a nice thing about functional programming. Okay, variables are only calculated when needed, and you don't need to pre-calculate variables. Values you don't use for. I mean, like objects. Okay, this one depends on how much you use the objects, but the main thing for functional programming is that the way we like to program is using pure functions. Pure functions have a set of inputs for self-outputs. Doesn't change, doesn't do anything, doesn't depend on the way you set the objects. For example, for this nonlinear resistor, I have to set parameters, and depending on these parameters I set in a nonlinear resistor, executing function within the nonlinear resistor class will, well, change. Yeah, so that's just something to keep in mind. Yeah, so it's functional programming makes it very easy to debug. So here are the strengths and weaknesses of each principle. Okay, so what's the ultimate principle for me when I do programming here? Okay, so I use the KISS principle. It stands for keep it simple stupid, but I of course don't endorse calling people stupid for no reason, or I try not to. Yeah, don't call people stupid. All right. Yeah, I try to live up. I may not do it all the time, but yes, don't do it. I try not to do it. Okay. Yeah, the principle of keeping things simple is very important. So don't introduce complexity when it's not needed. So where do I start? The most simple way of programming is to just talk about procedural programming. This is the simplest form. It's good for small bits of code, and by default I will use procedural programming first as far as possible. So in a sense, even when I instantiate classes, I don't want this class to be dependent on so many other classes. Okay, if I can write everything within one function within that class, I'll write it within one function within that class. I won't do anything else. Yeah. Okay, but of course that isn't realistic for big programs. There is a strength to object-oriented programming, and then there's a reason why it is taught in schools. Okay, I do expect the code to be patched or extended over time, so it's good to keep things modular. So this would require that almost things should be object-oriented by nature, and of course when I code, I expect to change things iteration after iteration. So how am I going to segregate how things change? Well, the way I like to do it is perhaps using interfaces. Okay, because interfaces, you only care about inputs and outputs of the code. You don't really do anything else with it, right? You don't do anything else with it. You just care about inputs and outputs. The underlying code will differ from the implementation to implementation. So yeah, for the parts where I really expect to swap out in and out the code a lot, I will use an interface. Okay, interface, factory style programming and all that. So for example, the pipe class that I make, will actually just probably inherit from this nonlinear resistor test.cs or nonlinear resistor.cs. Okay, nonlinear resistor component I parameterized. Yeah, so a pipe class will inherit from here, and of course I expect this pipe class to change a lot. So what will I do? And I maybe expect the dependencies of the pipe class to change a lot as well. Okay, so for those things I expect to swap in and out very often, I will use the interface interface class, so that at least when I want to maintain things, okay, and this is very good for object-oriented programming. If I want to maintain things and keep swapping things in and out, swapping parts of the code without damaging other parts, then this whole thing about loose coupling comes in very handy, and that's what it's good for. So where I expect things to swap around, dependencies to swap around a lot, I will put interfaces. Otherwise, don't bother. Just keep things procedural. Okay, reusability and modularity. Okay, I also want certain parts of my code to be reusable. That means part of my code can be functional. For example, the derivatives, the classes. The derivatives and central difference approximation. Those things are pretty generic enough that they can be pure functions, right? They can be pure functions. So in the sense that one input will always give you one output. So these I'll kind of cater these styles of programming to different parts of the code. So I'll start out with procedural programming. If I have bits of functions that I keep wanting to reuse, I will put in functional programming or object-oriented programming. Okay, object-oriented programming is the more heavyweight version, where I can do a lot more with swapping things in and out, swapping classes in and out, and swapping dependencies in and out. So that's what I will do. Okay, unfortunately C# is pretty object-oriented. It forces you to declare classes and all that. So even then, I will try to use, maybe I won't try to do too complicated a style. Just use pure functions within some of the classes, and that will kind of keep to the functional programming, so-called functional programming mindset, or what you call it, the functional programming thought process or school of thought as close as possible. Okay, the whole idea here is to keep it simple. Keep it simple. So I'll use procedural programming and functional programming as much as possible. If the code gets really big and I need to segregate the code into different classes under the same namespace, or even different namespaces or whatever, I'll just use object-oriented programming with interfaces and all that. Okay, so the application here is to have iterative programming with interfaces and the factory pattern. So the code, since I will have a lot of versions of for example, my pipe class, or have different versions of the Jacobian and all that. So each pipe, okay, I'll have several different versions, and they will sort of fulfill an abstract version of the class. So as you can see, okay, the nonlinear resistor here, I will just replace this nonlinear resistor with a pipe, okay, and then I'll change the underlying code within, okay. As you can see, this is nonlinear resistor actually inherits from component and I parameterized, okay, and you don't really see a I component interface here, even though it exists. So you can see that in over here, if you take a look at the center bits, if you take a look at spiceSharp, and you look at what am I looking for? Components. Okay, you'll see an I component interface right here. Okay, I component interface right here. Now, even with the I component interface, you can't really interact very much with the model, but the component class itself will implement the I component interface, and it's this thing called abstract class. Okay, and the thing about abstract class, long story short, is that yes, there is some level of implementation within the abstract class, but it can function almost the same way as an interface, in the sense that in the sense of the purpose, right? You have a class that you cannot use to declare an object, but there are certain sets of inputs and outputs that this thing is supposed to receive and give, and then you can make another class inherit from this component class, all right, and it's supposed to have a base set of functions that is supposed to be put in. Okay, so let me open this up, and yeah, you have this component connect, okay, and then you have this abstract classes, all of these things here, okay. So this I mean, using an abstract class as if it were an interface, I mean that's one of the ways of doing it. I mean, I'm not entirely sure of it, that we can just use abstract classes the way we use interfaces, but in a sense, making all the classes inherit from this abstract class, it's almost not really like using an interface, a common interface. The interface, of course, being component. Okay, but I mean, the abstract class is not an interface, but it can sort of functionally behave like one. Okay, because it gives you a way of interacting with different child classes in the same way. And as far as I know, in C++, there's no such thing as an interface. Okay, if you try to look for C++ interfaces, because I never saw interfaces in C++. Okay, you won't really find an interface keyword. Okay, but you will rather see them in abstract classes. So abstract classes are classes that are not fully defined. Okay, they are not fully defined. You cannot instantiate objects out of them, but essentially they are supposed to be so-called like interfaces. Alright, so we will use these abstract classes like interfaces. Okay, so we'll have the factory pattern that will instantiate the resulting objects, and I'll use the pipe code. I'll scaffold the pipe code of the custom resistor code, which you already see here. Okay, I'll go to spiceSharp test. Okay, spiceSharp test, and you go to spiceSharp test, and I'll go to custom resistor. Okay, and here we are. Yeah, I will use the same code as nonlinear resistor, and I'll start making a so-called yeah, I'll make pipe classes that more or less copy and paste this code, and then I'll work my way from there. Okay, and because we have so many versions of pipes, I'm going to iterate pipes, like maybe pipe version 1, pipe version 2, or pipe version of such and such date. Okay, I will have also a factory class. Okay, because I have many different implementations of the pipe classes, I will just use a factory pattern, meaning to say I have a class to help me instantiate the pipe class or build the pipe class, and that's what I will do. Okay, so the pipe class I want to assemble it using dependencies. Then maybe I will just apply a line of text that says, yes, please grant me this, give me this, grant me this object. Okay, grant me this object, and then the factory will construct everything, and then it will grant you the object. Okay, that's what the pipe class object factory thinks. So yeah, so I also plan out how the user will interact. Okay, so I will have a class that the factory class will be interacted with the user like that, or the factory class will have a return pipe method. Okay, the return type of the return pipe method, the return type or return class is component. Okay, is this abstract class of component. So instead of interfaces here, I will use the abstract class as the return type. Okay, and then I will use this return pipe. Okay, and then the user is supposed to pass in a string of the implementation that you want. Is it a pipe, a flat pipe, a pipe with elevation, a pipe with entrance effects, so on and so forth. I have all of that, and then the return pipe method will just grant the pipe object using the component type. And then of course I'll have a get list, which is it's a way of getting the pipe to the pipe factory class to get a list of the available component types that you can select and you can put in here. And get list will just return a list of valid pipes. Okay, and of course we want it to behave such that if we supply a wrong string in here, an exception is thrown, meaning to say I want to let the user see that there's an error. Okay, the proper term is called exception, and I want the exception message to tell the user which pipe types here are valid. Okay, and as far as possible, don't have it case sensitive. So that's whatever. And then over here we have under the hood constructor. Okay, so we're getting into nitty-gritty details now. So I will just stop for now. I will carry on more in these nitty-gritty details in the next video. Okay, see you next time.